Okay, guys, I've just gone through forces on inclined planes, resolution of force on inclined planes, and resolution of forces on horizontal planes. Now we're going to look at forces with connected masses on both inclined planes, on horizontal planes, or if they're connected via a taut string over a pulley. Okay, so here, applications of Newton's first and second laws with connected masses. So here we look at objects that are connected together with a rope, so maybe a truck pulling along a car with a taut rope between it. If we have two objects connected by a light inextensible string, or if they're coupled together like a trailer and a car, each object simultaneously will obey Newton's laws of motion. The tensile forces which act on the objects in the string are both equal in magnitude but in opposite directions. So, what does that mean in real terms? That means that if I had a truck pulling a car, so W2 is our truck, W1 is our car, the force that it's producing is pulling the truck along. The tension between the truck and the car produced in the rope or the tow rope, whatever's between it, these will be exactly the same magnitude. They'll just be in different directions. So this one will be pulling back on the truck, and this one will be, this one will be pulling back on the truck, and then this one will be pulling the car. We say on a smooth plane because we assume that there's no friction. A taut rope, so it's not springy or anything, it's held still. And generally they'll say that the weight is negligible. If we have a smooth pulley, the weight of the pulley is considered negligible. So this is negligible, and so is the weight of the strings. Likewise, it's always completely tense. The tension upwards here and the tension upwards is equal. So there's no loss of tension over the pulley. So it's assumed to be equal. We've got a weight force here downwards. And we've got another weight force here downwards. So it's always going to go down in the direction of the heavier weight force. The tensions in both sections of the rope can be considered equal. They're just in opposite directions. Okay, if I have a mass on an inclined plane, we have got our weight force downwards. So whatever the mass is times gravity. Our reaction force, which we would create a triangle and then work out what our reaction force is, because it's these two components. I would have R1 minus W1 is equal to 0. Once we work out R1, we can then use that here for friction. So it's all based on the angle. The angle's there. We can work out this component. We can work out our reaction force. We can then work out our friction. Of course, our tension between the two particles is going to be exactly the same. This one here, its tension will be the same as what the tension is at the front. Okay, so that's the tension of the string is equal to the magnitude in both sections. The inclined plane is rough, so it's got a friction force working on it. The next one, the body is accelerating down the plane. So if it's going down the plane, we know that our friction force is going to be going up the plane. We know that our weight force is going to be going down. Our tension up and our tension here is going to be exactly the same. Our weight force will be pulling down, but it will be accelerating upwards because the string's going that way. Okay, so you just got to remember, if it's going down the inclined plane, then the friction's going to be going up. If it's going up the inclined plane, the friction's going to be going against it. two masses on a smooth inclined plane, in general T1 doesn't equal T2. So here these two tensions are not equal. They could be, but in general, that like it's not assumed that they'll be exactly the same. So don't make that assumption. We've got our weight force, another weight force. Of course, these could have friction as well. So you could have friction if it was accelerating up the plane. Friction would be going minus mu r. Whereas if it was accelerating down the plane, then friction would be going up the plane. Okay. Here, we can consider that and that as one system to work out the tension here, like there. And then we consider that and that singularly to work out the tension between the two of them. Okay, so let's try and apply it. A car of mass, a ton, so 1,000 kilograms, and another car of mass, so 0.75. A car of mass 110 tows another car of mass 0.75 tons with a light tow rope. They say light because we don't want to worry about the weight. Okay, so I might actually draw it on the diagram because it'll make more sense. So this one's 1,000. This one's 750. We've got that S and T are equal because they have to be. So first thing we say S is equal to T. If we think of this as one full system, our mass is 1750 kg. Our force is 3,000 newtons. Resistance to motion can be neglected, so we've got no force from the ground. If towing the car exerts an attractive force of 3,000 newtons and the resistance to motion is nil, find the acceleration of the two cars and the tension in the rope. So we know force is equal to mass times acceleration. So we've got 3,000, that's not 3,000, equals 1750 A. So therefore, A is 3,000 on 1750, so 250 divides into both of those. I'm going to get 12 on 7 meters per second squared. So the whole system is accelerating to the right at 12 on 7 meters per second squared. Have I answered the question? Find the acceleration of the two cars and the tension in the rope. So our tension in the rope, we know this little thing here, we know that our force being applied, our force is mass times acceleration. So we need to work out our force. We've got our mass, which is 750 kilos. So our force is 750 times our acceleration, which is 12 on 7. So our force is 750 times 12 on 7. So 1286, 1285.71. 1285.71 newtons of force in the rope. And that kind of makes sense because we know if we've got 3,000 newtons of force going in that direction, forgot a zero. If that's a 1,000 kilo weight and that's a 750 kilo weight, it's going to be in a ratio of 1,750. So this force here we would think would be 750 out of 1,750 kilos times 3,000. 750 kilos out of the system, out of the full 1,750 kilos times the 3,000 Newton weight. 750 divided by 1,750 times 3,000 gives us the same value. So the amount of force being applied to this car is in a ratio of the weight between this car and then this truck. Of course, you can just work it out this way. Okay. Now we're going to look at a 2.4 kilogram mass on a smooth surface. So this is 2.4. That's 2.4 G. That's 1.2 G. Now, there's a light and extensible string, so that string is negligible. The tension there and there is going to be exactly the same. So, if we look at each force independently, there is no friction because it says it's on a smooth surface. So here, what are we going to have? So our normal force will be 2.4 G. Okay, so we've got tension this way. That's our force. That equals our mass, 2.4, times our acceleration. So that's this, the system here. We'll call that equation 1. Now this one here, this system, we've got T minus 1.2 G, because I've got my T upwards, and then I've got my 1.2 G downwards, and that's going to equal mass times acceleration, which is 1.4 times acceleration. That's equation 2. Draw a vector diagram. So these are our vector diagrams. The string passes over a frictionless pulley. So there's our frictionless pulley. So assume there's no friction, there's no weight. Calculate the acceleration of the system. So I've got T equals 2.4a and T minus 1.2g is equal to 1.4a. Okay, so what do we know? We can put T, that into this equation. So 2.4a minus 1.2g equals 1.4a. So therefore our acceleration of the system is 2.4 minus 1.4 is just 1a, and that equals 1.2 G. So did I stuff something up? A equals 1.2 G. How did I get 1.4? Where the hell did that come from? That's 1.2. So that is, where the hell did that come from? I think I copied it down wrong. Okay, so we've got, sorry about that, I just copied it down wrong. Okay, so we've got this system here, which is T is equal to mass times acceleration, equation 1. Then our second one, our vertical forces, T minus 1.2 G is equal to our mass, which is 1.2 times acceleration. Okay, so from here, let's replace t in here. So 2.4a minus 1.2g equals 1.2a. So then we get 1.2a, when I bring this over to the other side, is equal to 1.2g. So then a is equal to g. I've completely stuffed this up again. Okay, because, where's the rest of my page? Okay, that's a what not to do. I've got t is equal to 2.4a. That's from this system here. In this system here, we have got 1.2g going down. So 1.2g minus t is equal to 1.2. So we're assuming the system is accelerating that way. So t is to the right. So here, if tension is going, I'm going to have tension going that way for this system because it's accelerating to the right and then down. And then here, my tension is going to be going upwards. So this would be 1.2g minus t, 1.2g down, minus t up, and that equals 1.2 times my acceleration. Okay, that sounds better. Okay, now let's plug that 1 into 2. So you get 1.2g minus 2.4a is equal to 1.2a. So then from there, we can bring our a's to one side. 3.6a is equal to 1.2g. So therefore, a is equal to 1.2 divided by 3.6 is g on 3 meters per second squared. So it's accelerating down at 3. It couldn't be accelerating up because there's no force here to pull it in that direction. Yeah, I don't know what I was thinking just then. Okay, calculate the magnitude of tension in the string. So what have we got to do that? We know what our acceleration is. So we know that our tension, when it says magnitude, because you've got the tension going in 2 different directions. So I would have my tension is equal to 2.4 times g on 3. So t equals, how many 3's go into that? 0.8. So 8 on 10, 4/5 g newtons. Or, that's 4/5 of g. .84. So we've answered our questions. The first one, draw a vector diagram. So here, there's the particle that's on the flat plane. There's its weight force. There's its normal force or reaction force. There's our tension to the right. We've got tension going up in the other particle. And then we've got the weight force going down. Our acceleration is g on 3 meters per second squared. And our tension in the string, I'd probably leave it like this actually, 4/5 g, because it's an exact answer. Okay, this one looks like fun. So, let's look at each thing individually. The diagram shows 3 masses connected 4 kilos, 5 kilos, 11 kilos, connected by a light and extensible string, one of which passes over the pulley. The system is released from rest. Calculate the acceleration of the masses. Okay. Let's assume, because this is heavier, we're accelerating down here. So tension would be up, our acceleration would be down. So we can say 11 G minus my tension 1 is equal to mass times acceleration. Our mass is 11 times acceleration, so that's equation 1. Now, if we look at our 4 kilogram particle, we've got T1 up, which we know is going that way, so we know T1's got to be positive. So T1, what have we got hanging off that? We've got the 4 kilogram mass, and then we've also got tension 1 pulling down on it. So, tension 2, T2, and in this case here, our mass is 4, so 4 times our acceleration, so that's number 2. Lastly, let's have a look at this particle here. So we have T2 going up minus 5G going down, and our acceleration, our mass times our acceleration, is 5A. Okay, so from here, what can we do? We can use simultaneous equations and say, if we do 1 plus 2, what's going to happen? I think so if I do 1 plus 2, I got 11G minus 4G, which is 7G. I've got minus T1 plus T1, which cancels. And then I've got minus 2T. That equals 7A. We'll call that equation 4. Okay. Now, if we do... So that's 1 plus 2, and I've called that 4. Then if I do... What do we want to get rid of? We want to get rid of the T2s. So here, if we get rid of the T2s, if I add 3 plus 4, so I get T2 minus T2, they cancel, minus 5G plus 7G, which is 2G. That equals 5A plus 7A, 12A. So therefore A is equal to G on 6. What have I stuffed up? Oh, you idiot. When I added 11A and 4A, I didn't add them, I subtracted them. So here, we're going to get 15, no, here we're going to get 15A. No, we're not, wrong place. Having a good one. So we get 15A here. And then if I add them together again, okay. So here, if I add this one and this one, because I've got 2t minus 2t, they're going to cancel. Minus 5g plus 7g, which is 2g. 5a plus 15a is 20a. So therefore a equals g on 10 meters per second squared. So there's our acceleration of the masses. The tension in the string joining the 4 kilogram mass to the 11 kilogram mass. Okay, so we know T1, that's that tension there, that's the tension we want to find. What do we know? We got this equation, so we can just use that. I'm going to change back. Okay, so 11g minus T1 is equal to 11 times g on 10. So bring your tension to the other side, and the 11, so I've got 11G minus 11G on 10 is equal to T1. So I've got 110 on 10G minus 11G on 10 equals T1. So I would think that our tension is going to be 99 on 10G. That's what our T1 is. Or T1 equals 9.9 G newtons. So that's the tension in this one, this string. What did I say? 9.9 G newtons. Okay, T2, the easiest one to use is number 3. So we know T2 is equal to 5G plus 5A. So T2 is equal to 5G plus 5 times G on 10. T2 is 5G plus a half G, which is 5.5 G. 5.5 G, that's a fair bit of money. What's that? 11 on 2G. So that's our exact answer. Or we can say T2, we can just say 5.5 G, I guess. So that's how much tension is in this rope. T2 is equal to 5.5 G newtons. Forgot my newtons. Okay, so we got the acceleration of the system is G on 10 meters per second squared. So that's going that way. We got the tension in this rope is 9.9 G newtons, and the tension in the second rope, this one here between these two particles, is 5.5 G newtons. Okay, so that can be a little bit tricky. I stuffed up a couple of times with directions. Just think about which way the system is going to be accelerating and make sure you remember that. Yeah, I just fluffed it up then. So in this case here, we had our 11 kilogram force. So that was 11G going down. And then we had T1 going up, but we were saying the system is accelerating down. So 11G, did I put 10? 11G minus T1, that force up there, is equal to our 11 kilos mass times our acceleration. Then we went around here, and we know that T1 is going up. So we started with T1, we're accelerating that way, so that's positive, minus my 4 kilogram mass, so 4G, and then minus my tension, because it's going that way, and then our acceleration is 4 kilos, but it's going that way, so it's positive. And then lastly, we had our T2, which is going upwards, so we start with T2. We minus, because it's going in the opposite direction, 5G, our weight force, downwards, and the acceleration, the mass is 5 times acceleration, which it's accelerating that way, so that's considered positive because T2 is positive. Then, from using simultaneous equations, we got our acceleration, our tension in the string 1 and tension in the string 2. And don't forget, those tensions don't have to be the same. and generally they won't be the same. Okay, so hopefully you get an understanding of connected masses or connected particles. Don't forget to take into account if you've got an inclined plane and you've got friction. The main thing is drawing a good diagram and placing your forces on it, and then working from there. Okay, have a good day. Bye.